development sondado.
Okay.
Okay, so maybe we'll start. So like I will say this many times, June, like many other lectures in this summer school, will needs no introduction. So I won't introduce him except to say as a dear colleague and friend that it is an honor to work side by side with him and also socialize with him from time to time. So June's going to tell us about molecules and cold molecules and what else is on there. Let's see. Well, Anna Maria, can you help me out here? I don't see the schedule. Okay. Yeah, here's this. The official title is Molecules, Clocks, and Metrology. So we're looking forward to an exciting collection of frontier physics. Take it away, June.
Well, thank you, Leo. Certainly, it's an honor to be invited. I think the last time you invited me was 3 years ago, and I certainly enjoyed it at the time in-person lecturing with the summer school students. As Leo emphasized, it's more important that we interact. So even though the title sounded grandiose, and believe me, it's Leo's title, not mine. but I actually, because of Leo has such a commanding intellectual lead on us, I always try to do whatever Leo tells us to do. So I did prepare 2 lectures with lots of material, with molecules, which I will start today, and the clocks on Wednesday. However, considering the importance of interacting with you, and I think I would love to be interrupted and have a lot of questions being entertained. And if I don't get to finish my material today, I will just continue on Wednesday. And it's okay if by the end I tell you a little bit of the latest work in the clocks, and I don't have to cover all the material that I have prepared for you. It's more important to have fun together. So I will tell you some of the most recent progress of making a quantum gas of molecules. But maybe more importantly, the community has been working on ultracold molecules for the past 2 decades. And the one spirit I really want to share with you is finally the days is here where we can actually tune the interactions between molecules and realize a strongly interacting molecular system. And that's something we've been working towards, like atomic physics that you have heard about already this morning. And you will see some resemblance that finally dipolar quantum system molecules are coming of age to start to become real tools in the laboratory. So let me get started. You can all see my title slide, right?
Yes.
Yes. And I'm going to advance to the next slide. So just a very quick introduction, ultracold atomic matter. And I think you have heard great lectures already today from Eric and Antoine. But let me just make a very quick introduction. Ultracold atomic matter is interesting, partly because it gives you precise control of quantum systems, allow you to make clocks, quantum information processors, sensors, and etc. Allow you to probe complexity and the strong correlations, especially when the interactions can be tunable, especially when these individual particles can be programmed. And that really underlies many of the recent excitement of the quantum revolution. And also, of course, studying physics, an interesting area has always been when you study particular subsystems, how universal is it? Is it scalable? And you know, one of the interesting area of quantum simulation has always been, we got ultracold atoms confining optical lattices. Can you use this to simulate condensed matter systems, even though the energy scale or density of the system is completely different, but can we scale that altogether so that you can uncover some deep insights in some of the outstanding condensed matter problems using ultracold atom or molecular systems. And as you have heard, I'm sure, no doubt today, as one of the early pioneers of quantum gases, Eric Cornell created these Bose-Einstein condensate. You will hear from the public lecture of Wolfgang Kadelin tomorrow. And typically you have a system where atoms are cooled down to a few hundreds of nanokelvin. You have about 1 million atoms. The spatial density is roughly 10 to the 12, 10 to the 14 per cc. And that's a rough scale of the quantum particles you want to have. The most important aspect when you so-called quantum gas is the the Broglie wavelength of individual particles start to overlap with each other. And so when I say quantum gas of molecules, we have now cooled the molecules down where individual de Broglie wavelengths of molecules now overlap with each other. And it has already given rise to a number of striking phenomena people can observe in the laboratory, like such as a superfluidity, both fermions and bosons. People now can image individual atoms and look at the magnetic ordering, transport properties in the cold atom systems. You can look at it, for example, when you're pairing up fermions into BEC, you can study the BEC-BCS crossovers, study the fermionic superfluidity, and so on. And perhaps you can already guess the two most important ingredients in all of these things, realizing laboratory control, is very precise control of atomic interactions, whether you can tune it with a magnetic field, or in the case of molecules I'm going to tell you about, tune it with electric field. And also you can control atomic motion by cooling them, by putting them in the optical lattices and so on, by controlling this tunneling rate between the lattice sites. Once you can control these atomic interaction and emotional degrees of freedom, you can create these exotic quantum phenomena, create these correlations, and really has opening up an intellectually rich playground for both precision measurements, metrology, which I love, but also condensed matter, many-body physics, and so on. That this deep connection between metrology and the quantum information and the quantum many-body physics is very enriching. So why cold molecules? Atoms, we enjoy these contact interaction. They approach each other. You have so-called isotropic van der Waals interactions typically. Of course, you heard about Rydberg atoms now, and they are magnetic atoms. So this, of course, is not absolute truth. People are very creative. They can come up with ways to control atomic interactions. The molecules early on, from about 20 years ago, when we start to work on molecules, it comes with this feature where you got electrical dipoles. The molecules can be easily polarized under the laboratory frame using a fairly simple electric field. And then you have these dipole interactions, electrical dipole interaction that's anisotropic, as I shown down there, 1 minus 3 cosine squared theta. It's tunable, and it can be very strong in the long range. And the question is, can we realize molecular systems where for the longest period of time, we just have been fighting the battle against loss, because these molecules just love to have chemistry, love to have chemical reaction losses. And finally, we can now control them so that you can tune on these interactions and actually use this to study dynamics. And dipolar quantum systems, very early on, we envisioned the quantum systems where, for example, on the right-hand side, it's showing a stack of pancakes where molecules are individually controlled under electric field. And I'm happy to report to you towards the end of my lecture, if I get to there, we have now realized such quantum systems that you will have individual controls of individual pancakes, and you can actually see these molecules jumping back and forth. The molecules themselves do not jump, but their spin excitation can jump back and forth, and you can actually observe interesting dynamics. And so these are new quantum systems we can create in the near future, bi-layer systems for you, tri-layer, and you name it, with the different angular orientations and different internal degrees of freedom. So really create a new quantum systems for you to study. And of course, as you will be learning in the summer school, people have played with atomic magnetic dipoles, and you will say, what's the difference between the atomic magnetic dipole and electrical dipoles of molecules? And they all both dipolar system? Yes, very much so. With a small differences where if you use one debye to characterize normal size of electrical dipole versus a Bohr magneton to characterize the normal size of magnetic dipoles in an atom, the strength of electrical dipole is actually quite much bigger. But one can make argument, I can find an atom with 10 Bohr magnetons and so on. So that's not really the point. The point of if a good experimentalist with the help of theorists can always find a quantum system, even if the interaction is weak, they can just make a quantum coherence live really long, such that weak interaction can still manifest as a strong interaction. But what's really important is the tunability, because you have a Hamiltonian. You want to see if you were able to control the interaction strength, if you can control the anisotropic properties, and so on. And there is one key difference between electrical dipole and the magnetic dipole, is that magnetic dipole is always there. It's a current that's existing in the atomic states. But electrical dipole actually violates the so-called time reversal symmetry. You actually have to apply an electrical field in the laboratory to induce that electrical dipole moment. That means the dipole moment strength itself is completely tunable, both in terms of angle and the strength. And that's the area that I'm going to show you some of the recent results that we take advantage of that. But molecules are very complex. And that's, of course, the reason why we are a decade or two behind, maybe 2 decades behind atomic physics. And that's because molecules have a range of degrees of freedom, ranging from electronic degrees of freedom that, of course, creates a binding energy. The nuclei can vibrate, rotate around each other, and you have a spin-spin, nuclear spin interactions, so-called hyperfine structure. All of that, some of the atomic physics has electronic energy, has in hyperfine interactions, but you don't have, 2 nuclei rotating around each other, and that electron is trying to create potentials to adapt to this molecular motion and so on. And so this extra degrees of freedom, vibration, rotation, carries a lot of energy scales, but also more importantly, it has a lot of places where entropy can go into. And the energy scale spans many orders of magnitude, ranging from electronic energy of a binding energy of a molecule to all the way to when you're trying to create quantum gas of molecules, where when we start to talk about the Broglie wavelengths of individual molecules overlap with each other. So the temperature of these molecules needs to be cooled down to a few hundreds of nanokelvin. That spans 10 orders of magnitude, but the energy is not something that we are worried about. We can use laser photons to control these energy scales. It's the entropy. If you have gone into the laboratory to become rudimentary spectroscopists, that's how we all get started in the AMO lab, is do some sort of spectroscopy. And that's key difference between molecular spectroscopy and atomic spectroscopy. You look at the line on the left-hand side, you'll see just lines, millions of lines, and that represents all these degrees of freedom: electronic, vibrational, rotational, hyperfine, and so on. So imagine that you're trying to create a quantum gas of a molecule where every molecule behaves exactly the same way. So that's a lot of entropy you have to squeeze out of the system. And so over the years, people have invented various different techniques. This was actually a review article we wrote more than 10 years ago. The vertical axis represents the density in log scale, spatial density, and the horizontal axis.
I think you have a question in the chat, so maybe I suggest the students just to speak out loud so it's easier for Jun to hear.
Oh, actually, Anna Maria, this is great. If you don't mind to play a role to stop me, like you just did, that's perfect. Can you actually? I can't see the chat.
Yes, they said 2 electric dipoles still have to be induced even if the molecules has large natural dipole moment.
Yeah, that's actually a very interesting question. You probably heard from Eric. I don't know if he mentioned about he searches electrical dipole moment of electron, and so you asked this very natural question. Well, molecules didn't we get taught that molecules already have permanent dipole moment? What are you talking about? You need an electric field. It's actually true that the molecules possess electrical dipole moment permanently, but it only lives on its molecular frame. So if you don't mind, live on the molecular frame, tumbling with it, and getting all dizzy and also on, you will have an electrical dipole moment there. The problem is, without a laboratory-defined frame, electric field, the molecule just has no predefined direction so in the laboratory frame, your friend, you jumped onto the molecular bandwagon, but your friend stays in the laboratory frame. The friend looks at you and you're just tumbling all over the place. And on average, you have no dipole moment. And that's really what I'm talking about. In the laboratory, when you're trying to control a dipolar system, you have to use electrical field to induce a mixing of these 2 fundamental quantum states. And that mixing of opposite parity creates a dipole moment that's measurable and appreciable in the laboratory frame. Does that answer your question? If not, just keep asking.
Can I connect to an earlier lecture? So we had Antoine talk about Rydberg atoms today. And I think you can think of the molecule as very similar to the molecule of a nucleus, a positively charged nucleus, and a negatively charged electron. So there's a sort of mapping between the Rydbergs and molecules where they can both profitably be viewed in this way.
Yes, and complementing what Kaden was saying, if you don't have an electric field, you can have a dipole moment when you have a superposition, like he was explaining that today too. Mm-hmm.
Yeah, and it's all about the frame transformation, right? You can have a coherent superposition of excited ground state, and in that coherent superposition, there is a dipole. It's actually oscillating back and forth. But again, these you have to be jumping onto that microwave frequency spectrum or optical frequency spectrum, actually watching it. Otherwise, you are going to average that away. And so that's really the key point.
And following that, and if you are only in excited state, no superposition, does it give you a permanent dipole moment then?
No. So yes, Anna, thank you for asking that. That maybe another point I should make is if you are in a single quantum state, just think about it. If you're in a single quantum state, you ask yourself, can I have a specific orientation towards this in space? You cannot, because if you do, you can actually violate the reversal symmetry. So you always have to somehow mix two opposite parity states to create a dipole moment. And that is very different from magnetic moment. In magnetic moment, you can have a persistent current running in a single quantum state. Like you said, excited state, some excited state of atoms has magnetic moment. And that's because there's a persistent current running around, right? And that's very different from electrical dipole moment. It doesn't have electrical dipole moment unless you have a field that you apply to break that symmetry. And however, of course, in the deep down in the so-called standard model, they had to introduce some sort of a symmetry breaking component into the framework of the standard model to explain some of the degrees of freedom in the weakly violating parity violation. But that violation is actually not big enough to explain, for example, the asymmetry between matter and antimatter, or you cannot use to explain the reason why the time reversal symmetry violation is actually much stronger than the parity violation. So this is actually you can say there is some fundamental physics that explains this kind of a symmetry violation with permanent dipole moment of electron. That's like as a single quantum state as it gets. But that's at a level of 10 to the minus 40 electron coulomb, coulomb centimeter level. And in order to the current test that allow you to place the limit of 10 to minus 30, 10 orders of magnitude away from the standard model. So it's pretty good, and people haven't found existing electron dipole moment yet. So it's pretty good limit at this point that you can assume, especially you're trying to simulate condensed matter system, you're trying to tune the interactions, you can pretty much assume that if you don't turn on electric field in the lab frame, you won't have electron dipole moment. Okay. Should I get going?
Yes, thank you.
Thank you. Thank you for this interesting discussion. So the technology of making molecules, I was just at that point. People have come up with various different techniques, buffer gas cooling and stock deceleration using spatially inhomogeneous electric field to try to slow down molecules and so on. Even laser cooling is now working, that we can actually cool the molecules down to microkelvin now. So almost like the early 80s when the people invented laser cooling of atoms. So it's actually quite exciting. We can start to laser cool a selection of molecules. At the moment, just a few of them, but there are papers written even back in 2008. There's this class of molecules we identified that you can laser cool. That's been starting to work. But what I'm going to focus on today is to tell you a particular set of experiments now that's being actually taken up by many laboratories worldwide, where you're assembling atoms together to form a molecule. And because we are so good in making quantum gas of atoms, we can actually make now quantum gas of molecules recently. There's another comment came in, right?
Yeah, so this is from Michael Hyman. He says there can still be dipole physics between molecules without an external field though, right? Naively, the Hamiltonian has a 1 minus 3 cos squared theta term, and I'd expect the cosine term would average to 1/2 if there's no external aligning E field.
If you that rectification effect, you would have to have some sort of, how do you guarantee that the molecules coming together? So now let's think about, if we apply a rotational, you prepare some coherent superposition of states, then you actually have a dipole indeed. But in order to prepare a coherent superposition, you have to apply a field, a microwave field to prepare coherent superposition. And then you can argue, well, I'm not going to take that field away. And these molecules are precessing because they were driven initially by some sort of electrical field to create them an alignment. And that alignment do not go away indeed. There's a quantum coherence associated with two quantum states getting into superposition. And if you prepared all of your neighboring atoms in the same coherent superposition, and you take the field away, indeed, you have dipolar interactions going on there in that moving frame. And I think that's unfair to say you have not applied electric field. The electric field application is like a quenching the quantum state where you let it go. You create a quantum mechanical coherent superposition of two opposite parity states. And within their coherence time, there will be interactions that you can describe as dipolar interaction. Okay.
Yes, I see. Thank you.
Yes, thank you.
Thank you very much, Kaden and Anna-Maria. Just this is great. Like, if you could help me mediate, I really appreciate it. So like, with the only drawback is you are forced to be listening to things you already know very, very well. So sorry about that.
That's our job. That's what we do.
Yeah.
Okay. Well, thank you, professors. So now I'm going to talk about this. And actually, this goes back to the work we did 12 years ago, 13 years ago, and this approach is taking two quantum degenerate gases of atoms and molecules. This, in our particular case, was bosons and fermions, and then we bring them together and use this approach called a Feshbach resonance to create loosely bound molecular state. And you use a pair of lasers to do coherent quantum state transfer from this loosely bound state into a deeply bound low vibrational ground state, and thus create a molecule, which is a KRB molecule. And because you're pairing a fermion and a boson, so it's KRB molecule itself is a fermion, has a dipole moment of 1/2 the pi. This approach has not been taken up by many, many labs. I think the list listed here is not even exhaustive. And particularly now 2 laboratories, our lab and MPQ, Emmanuel Bloch's lab, have created quantum gas of molecules. The early work in 2008, we created molecules with temperature of 200 nanokelvin, density of 10 to the 12 per centimeter cube. And because they are fermions, we use Fermi temperature to describe how deeply it's degenerate. And it's the 1.4. So it's, as you know, it's still far away from quantum degeneracy, but it's close. We call it molecules getting to the quantum regime. At that time, we actually jumped phase space density by many orders of magnitude using this particular approach of creating molecules. And this is also an opportunity I want to, everyone in cold atoms should remember this phase. Our great colleague, Debbie Jing, who was instrumental in getting this collaboration started. She passed away, but she has been the king of fermion, the queen, I should say. I'm sorry about that, but She's the queen of fermions, but also molecules. And I just want to remember that for some of the youngsters who may have not remembered all the story, although you probably know now, one of the biggest prize in APS is actually Deborah Jane's thesis prize that we all hope our students can win. So just to very briefly, you can think about Feshbach molecules as just a simple tool where when the atoms are having magnetic interactions, you can use a magnet to control their magnetic interactions, like Z-man energy levels. And when they come together, have molecular potential, the so-called van der Waals potential, it means they can form a bound state. But that relative position between the bound state, one of the particular bound state near the dissociation limit, and the free atom energy when the two rubidium atom, potassium atom coming together and use a magnetic field to control their Z-man energy, you can actually find a particular magnetic field where the incoming free particle, the pairs of free particles, their incoming energy is on resonance with the bound energy of behind this van der Waals potential. And because of this, of course, that involves a spin flip, right? Otherwise, you will say, how can I, two atoms coming together, you form a binding energy. The free energy is always above the binding energy. But if you involve a spin flip, the Z-man energy can allow you to take away the energy difference. So when you hit that resonance, the scattering rates goes way up. The atom becomes really interacting. But what I care about here is you form this loosely bound molecule that looks like just below the dissociation limit. So you have finally a loosely bound molecules. It does not have really any dipole moment because they are so far away from each other, and they're extremely easy to be lost because they are really feeble. They're barely hanging onto each other with a binding energy on the scale of tens of kilohertz or 100 kilohertz and so on. And it's still far away from the absolute ground state. And then we use a pair of laser photons that we say that, well, we are going to excite this to some sort of excited state. Before the excited state can decay, we will immediately de-excite it into the ground state. And I'm describing the process as if we actually put a population in the excited state. In the real experiment, we actually reverse this order. We create quantum coherence between the excited state and the ground state. And then we excite the molecules from the Feshbach molecule state directly into the ground state without ever, in fact, populating the intermediate excited state. Therefore, we avoid altogether the incoherent process of going to the excited state. And this coherent state transfer just requires these two photons, one at 970 nanometer, the other one 690 nanometer for our particular molecule. But in fact, there are many, many groups now working with different bio-alkali combinations, and they all use this particular principle and schemes to do the energy transfer. And this energy transfer can be quite excellent, because you can carry away all the energies without increasing entropy, because the process is 90% efficient in its coherence. So we create the molecules in the absolute rotational vibrational ground state. Well, there's a nuclear spins associated with these atoms. And in fact, there are 36 nuclear spin states. And all I want to tell you is that not only we can transfer all the population to the absolute rotational vibrational ground state, we can also move the molecules into the absolute hyperfine ground state. Okay, so at this point, you will say the job is done. We were able to create molecules in the lowest energy state possible, electronic, vibrational, rotational, and hyperfine. And you can create these molecules in a trap made by the light. And you have already heard about optical trapping of atoms. So you expect to have really long lifetime, especially when temperature is so low. But what we observe is that in fact, the lifetime is limited to only about a second. And if you look at the evolution of the density of the molecules, you see this very clear so-called two-body loss when N represents the molecular density, and you can see its time derivative is proportional to a loss rate coefficient beta times the density squared, indicating two molecules coming together have some sort of a reaction and gets lost. And this process in fact, can be described as KIB plus KIB having chemical reactions to K2 plus rubidium-2. This was rather...
You have you have one question in the chat. Is how to avoid losing large number of molecules during each of these steps?
Okay. During each of the steps of the association, right? So then the Feshbach molecule is processed. When you create the molecules, when you create Feshbach molecules, you can then immediately try to transfer them into the ground state. And that process, if the entropy is matched well between the two different atomic species, if the time scale is done, on the order of a millisecond, you can actually keep the Feshbach molecules mostly alive. There will be some process of loss involved because atoms can collide with Feshbach molecules, killing some of those. But we can do as good a job as converting most of the Feshbach molecules to ground state. And then the laser transfer itself, that efficiency is limited by how well you line all the laser beams on top of each other, how well you control the coherence. And that's why it's limited to about 90%, 92% of the efficiency. Finally, you get to the ground state. And that's what I'm talking about. There is, once we get to the ground state, we thought things are going to settle down, right? You've gone through all these high peak hiking. You finally came back to the base camp. You're ready to rest. But no, there's a loss going on in the ground state. And that's the problem that I'm going to tell you. In fact, that's a problem that has plagued our field for the past 10 years. That's always been the loss problem. And only recently we were able to solve this.
And Jun, there is an associated question that says, would the energy released from the bound state formation heat up the condensate?
Yes, absolutely. Yeah, so loss is just bad. If the molecules start to lose, it kind of gets explosion going, because when the molecules, as they leave the trap, they're going to hit their partners and so on. So even without chemistry, the kinetic energy is sufficiently large to release all the atoms, molecules from the trap.
But these are fermions, just to clarify.
These are fermions. However, once they start to have chemical reactions, they turn into their product is no longer fermions. Yeah. So the key, I mean, the whole lecture really is about how do we control this loss, because it's been, I would say, up to 2020, this loss has been, I'm going to show you a slide. It's actually very universal in all molecules people have created so far, and it's been the major obstacle to solve. Because, we have been thinking ahead of, okay, we can study molecules, using molecules to study incredible correlations between different areas of the molecular gas, or putting them in the optical lattices and so on. And believe me, some of the teachers here, whether it's Leo or Caden or Anna Maria, they were far ahead. They gave us a lot of pressure because they said, you got molecules now, show us, here's the physics. So we are writing down superfluidity and simulate these with molecules, and we couldn't do it. And for the biggest reason we couldn't do it for 10 years is because of this loss problem that you are identifying. Okay, well, let me just give you one brief thing to remind you of the quantum mechanics you took in the classroom called collisions between identical fermions. Anna Maria emphasized these are fermions, and when the temperature is really low, particles behave like waves. The angular momentum, we used to use so-called impact parameters to describe collisions between classical particles. But of course, in quantum mechanics, we have to use so-called partial waves to describe this collisional process. If the angular momentum, the orbital angular momentum is symmetrical, you have S wave, D wave. If it's anti-symmetrical, you have P wave, and so on, G wave. So these are the quantum mechanical partial wave description of the process of angular momentum. Needs to have 1 or n units, integer units of h bar. Third, quantum statistics really matter. For fermions, the difference between fermions and bosons is the symmetrization versus anti-symmetrization between the exchange of the two particles. So for fermions, you have this minus sign. But because of this minus sign, meaning S wave is not possible, D wave collision is not possible, the first lowest order partial wave is a P wave with a 1 h bar unit of angular momentum. If you have 1 h bar unit of angular momentum, you all know that's got a centrifugal barrier, and therefore the collisional landscape looks like this, almost looks like a volcano, because there's fairly large centrifugal barrier for KIB, it's actually 24 microkelvin. It's relatively large. Large is always relative, right? Compared to when the temperatures cool down to a few hundreds of nanokelvin. Microkelvin, and that 24 microkelvin is a large barrier. So now we can study the mechanism of loss, and turns out it's actually very, very simple physics. People like Paul Julian and John Bone and so on, early on in the 2010, helped us figure this out. Essentially, the idea is that you have this 1 h bar unit of angular momentum that gives rise to the centrifugal barrier. But KIB and KIB come together, they can have this so-called exothermic reaction, release K2 and RB2. That exothermic means the energy is allowed. The K2 plus RB2 energy is lower than KIB plus KIB. And so if you have two molecules prepared at very low temperatures as identical fermions, then this molecule would have to, at 100 nanokelvin, would have to penetrate through the barrier, tunnel behind the barrier, have chemical reactions. And this tunneling rate is proportional to the temperature of these molecules. Therefore, you can actually describe the rate of the reaction proportional to the temperature when you're prepared in these in this quantum regime. Now, remember I told you we have nuclear spins. You can actually go inside and flip one of these partners' nuclear spins so that the two molecules now look distinguishable because they have different nuclear spin states. Suddenly, these are distinguishable particles. You no longer have the anti-symmetrization requirement for identical fermions, and therefore this barrier disappears. And these so-called S-wave collision can now come together, and they do not enjoy the suppression anymore. The rate can be 100 times higher.
Jun, question?
Yes.
So the question is, why is the rate proportional to T instead of e to the minus energy over T, activation energy over T?
It's because it's the so-called a near threshold. And so the energy is actually very close. The collisional energy is close to the barrier. And there you can just describe this collisional amplitude as proportional to the velocity, and therefore the rate is proportional to T. So I just described the S wave. I mean, these we can actually have, if you're interested, I can dig out equations for you. Maybe as a homework, although I was told you're already very, very busy, but we can do some homework if you like.
I mean, maybe simply it's just a quantum tunneling means you don't need the thermal activation, right?
Yeah, exactly.
Yes, it's low energy collisions and this is overcoming the centrifugal barrier. So you have the P wave interactions that the S wave are characterized by the scattering length. The P wave is characterized by the scattering volume times the temperature. Well,
yeah. And it's I think the statement, the Caden said is really like the activation barrier, all these things comes from the intuition of thermophysics, thermodynamics. And that's what's so interesting when we study these molecules. Eventually now we are winning some fans from physical chemists, from chemists who I do not claim to understand very much chemistry, but they're actually very intrigued by this. In near the absolute zero sort of a temperature landscape, and you study, you see these interesting chemical reaction rates as very different from the classical chemistry, where in classical chemistry, people talk about quantum chemistry, but quantum chemistry is all about electrons being quantum. It's never been the molecules themselves were quantum, So this is a very different. Right now, you have to treat the entire molecule as a quantum mechanical, how they approach each other, how they react with each other, and so on. So when we did this experiment, when we flip a nuclear spin,
so I don't know if you saw, but Kong Quinn had a review article on quantum chemistry with ultracold molecules just a couple days ago, I think, on the archive. So I put that in the chat for people.
That's wonderful. And this is really interesting right here. What John Bone said at the time, 10 years ago, when we flipped the nuclear spin and the chemical reaction just went crazy. A little, he called it a little pico EV control results in an EV energy release or something like that. That because of it's all about a quantum mechanical sort of a statistics and partial waves and so on that dictates all these reaction rates. Okay, and so if we summarize these so-called Wigner's threshold law, in the case when you have identical fermions, that you have these partial wave barrier, P wave partial wave barrier, and you see this rate proportional to T. And when you flip a nuclear spin, when it becomes distinguishable particles, then suddenly the rate is no longer dependent on temperature, and it's just a constant, but it's 100 times higher than the P wave reaction. I will come back to this point later because the loss rate is such an important thing. And it turns out, okay, no, thank you, Kang-Kun. Kaden just said Kang-Kun wrote a review article. I'm sure she talks about this because Kang-Kun was involved. She was a student in JILA. She was involved in those early generation experiments. And one of the things that she always wanted to do when she left here and became a professor in Harvard was, I want to find out what's the heck going on in the intermediate state when, you know, she was not happy with just KRB plus KRB turned into K2 plus RB2. She wants to find out about all these intermediates, because nothing happens suddenly, right? Everything always, as long as you have a good clock, a good measurement device, you always will be able to find out microscopically what's going on. And that's what she's trying to do. She's trying to find out these microscopic intermediate states. And the sum of her work really paints this picture that this kind of a chemical reaction is universal. You know, you have these intermediate states being formed and they are unstable, they dissociate out, and she can measure the lifetime. And I think that another really intriguing experiment was done by another former JILA student, postdoc at the time, Jun Ye, who now has his lab in Hong Kong, and he observed a very interesting experiment where he created sodium rubidium molecules. And the sodium rubidium molecules is supposed to be endothermic. If you created absolute ground state of sodium rubidium, then they are not supposed to have chemical reactions. And so this idea of, well, I can put sodium rubidium into the vibrational excited state, V equals to 1, then they will have a reaction. But if I turn them into V equals to 0, V represents the vibrational quantum mechanical state, then that reaction should turn off. Well, in reality, when you look at the experiment, they look right on top of each other. So something's telling you, you know, once the two molecules, the long range physics, which is dictated by quantum statistics, by the van der Waals interactions and so on, once that's fairly universal. Once they get close to each other, the short range of physics, which dictates whether it's endothermic or exothermic, is happening at a scale that I have to say right now it's not completely understood. Why? Because supposedly V equals to 1, V equals to 0 should be very different. If you just use the classical sort of a chemistry point of view, there's endothermic versus ectothermic differences. So this puts an interesting question, right? When Jun published this work in 2018, we were like, and the whole community was thinking about, well, the molecule is going to be really tough. They're just going to have reactions no matter what. And we thought we can create bialkalis, which are mostly endothermic, so you wouldn't have these problems, but it's having these problems. So now I'm going to advance to the current time, 2019 and 2020, where we finally were able to produce a degenerate Fermi gas of molecules. And I want to look at this loss process again. So the 2019 work that we produced actual degenerate gas of the Fermi molecules of the KRB. The success lies in we just went ahead to build a new machine and it produced a much larger number of fermions and bosons together. And so we were able to eventually use atom molecule thermalization technique, create a molecule of 30,000 molecules at 50 nanokelvin with a T over TF 0.3, now very comfortably below the quantum degeneracy compared to the previous T over TF 1.4. It's only a factor of 5 difference, but it took more than 10 years to do it. It's just a hard experiment. And I'm glad to report that now, as I mentioned earlier, that the MPQ group has also got into the quantum degeneracy. And just a very quick about atom molecule thermalization. You can actually demonstrate the atom molecule thermalization by, for example, producing molecule first, removing all the remaining bosons like rubidium because they tend to kill KRB. And then we excite the center of mass oscillation of the molecule, but we keep the very ultra-cold fermions there. And you can actually see as you, depending on how much fermions you have, you will see this oscillation of molecular oscillation gets damped out due to their collisions with atoms. So this is a direct measurement of the thermalization rate between atoms and molecules. So this is also part of the process why you can create these molecules and yet being actually thermalized within the atomic gas system to create right into the quantum degeneracy. And I want to also mention Wolfgang Ketterle, your public speech speaker tomorrow. His lab recently also demonstrated thermalization between sodium-lithium atoms. In their case, sodium-lithium molecules, in that case, a triplet molecule, not a ground state molecule, can thermalize with the sodium atoms.
Jun, in these experiments, is KRB in the thermalization experiments, is KRB in the ground state, vibrational ground state, or
these thermalization experiments we performed, Leo, in the Feshbach state, but because once the Feshbach state is fully thermalized, the conversion efficiency from KRB star to KRB is so good. You know, you can, once you have a coherent quantum mechanical object being created, if the entire process is coherent, then of course the object you created itself is also quantum mechanical degenerate. But to really answer your question even more rigorously, I have prepared the next slide, which is the, you know, so if you want to say, I want to completely prove that the ground state KRB molecules is a fully Fermi degenerate. Well, one thing you can study is the so-called poly-blocking effect. The fermions like to avoid each other. So if you get into the Fermi degeneracy, the density fluctuation becomes suppressed. And this is quite striking. If you look at this, for example, on the left-hand side, the image of the molecules, you can study the center of the image, where the molecule density is very high, versus on the edge of the density is relatively low. And on the edge, which is moving towards the thermal, you will have a higher density fluctuations just because you start to have holes. In the middle, when you have a high density, the likelihood of all the quantum states being filled up is very high. Therefore, the density fluctuation becomes really low. And so the density fluctuation variance proportion divided by the total particle number n in the thermal gas equals to 1. But if in the Fermi gas is proportional to temperature of T over Tf. So as you go to lower, better degeneracy, lower temperature, the fluctuation gets more and more suppressed. And so we can directly measure that. You know, this is actually the comparison between KRB star, Feshbach molecule, versus KRB, which is in the ground state molecule. And you can see that KRB indeed has a little bit more fluctuation than KRB star because the conversion efficiency takes away 10% of the molecules being deleted. So Leo, does that answer your question?
Open symbols?
Sorry? Oh, open symbol.
What are the open symbols?
Open symbol is like if they are thermal. So the suppression is not there. If you're not degenerate.
I see. I see. Thank you.
Jun, in Emmanuel's group, there are always also fermions, or the molecules that they generated are fermionic or bosonic?
Whose group?
In Emmanuel, in
Emmanuel's group is also fermion.
Oh, just fermionic. And Wolfram is also the thermalization. He's also looking.
I think Wolfgang's is actually boson.
Bosons. Okay, that's what I got confused. Okay, okay.
Wolfgang's is triplet, and Emmanuel's is actually real ground state molecule.
Okay. Mm-hmm.
So now let's revisit chemistry near absolute zero. I'm just going to just give you a quick summary. Remember we did this, right? That you studied the dn dt is minus beta n squared, and the beta rate coefficient is constant times temperature. If you plot beta over t, then you should have a constant. And this is what we did in with the thermal gas of a KRB. When we started to study reactions in degeneracy, we actually observed two interesting set of data. One is if you plot beta as a function of initial temperature, you see, because it's a semi-log, so this red curve is actually a linear scale as in previous slide here. But here, because it's semi-log, it looks like a little curved. But that describes data when the temperature is still above Fermi degeneracy. And when the T over TF is less than 0.6, then suddenly you have actually a reaction that's a sublinear behavior, that indicating the reaction is actually suppressed further. If I plot this more like normalized by temperature beta over T, remember that should be a constant, and indeed that's what we see. It's a constant if a T over TF greater than 0.6, indicating thermal gas. But when the T over TF is less than 0.6, when you get into the quantum degeneracy, that the chemical reaction actually gets suppressed by a factor of 2 or 3. And this, again, is something that Anna Maria Ray's group and the Chizo's group in Purdue have come up with some theories to explain that behavior. And we needed to do more experiments and the theory investigations together to really get to the bottom of the actual mechanism. I think the Anna Maria Ray's group and the Chizo's group have different theoretical mechanisms to explain this suppression. The one good thing is, of course, there is a suppression. So as you get into degeneracy, there's suppression. Well, that's good. That's good news. The problem, however, that we want to turn on electric field. Remember, this goes back to your very first question from the student. Well, if you enjoy the dipolar interactions of these molecules, you need to turn on electric field. As soon as you turn on electric field, what happens? Well, the inelastic collision rates just goes up the roof. And here is a study, again, Jun Ye, when she was a graduate student here in JILA, studied the beta of a T as a function of a dipole moment. As you induce the dipole moment in the laboratory from 0 all the way out to 0.1, 0.2 divide. And this is in log scale. So you can see the rate is going up by 2 orders of magnitude by increasing dipole by factor of 2 from 0.1 to 0.2. And the reason of this is because as soon as you turn on electric field, the previous isotropic landscape, that's the volcano kind of landscape, gets very anisotropic. There's a dipole interaction that's going to, all the molecules are going to be aligned with respect to the electric field. But the molecules can collide head to tail, which they attract each other, or side by side, which they repel. And this head to tail attraction overwhelms the barrier that is established by the centrifugal distortion. And therefore the molecules can just go penetrate through this hole and have a grand old days of a chemical reactions. So dipolar interaction enhance the reaction in the 3-dimensional gas. And this is exactly what we observe. So now you can get depressed. Well, I prepared all these molecules with all this effort and put it into the quantum degeneracy. Now, finally, I say, I want to implement some of the Hamiltonians that Caden Hazard has been telling us. But as soon as turn on electric field, the molecules get lost, right? And that it's actually very understandable. You can actually fit this extremely well, understand this. You know, you have these centrifugal barrier on the first term on the long range of potential. You have the C6 over R6 van der Waals interaction. This is what you see. But then you turn on dipole moment, the C3 terms start to become dominant. And apparently the attractive dipole-dipole interactions gave rise to the D to the 6th power. And this requires some derivation that was done by Gouvin-Colmenaire. But it's actually very well used to describe the experimental observations here. So questions here? If not, I'm going to move on finally to tell you something about how we solved all these problems. And okay, if you don't stop me, I'm just
sorry to interrupt.
Go ahead.
Yeah, my internet is a little bit flaky now, but if you can hear me, can you hear me?
I can hear you.
Yeah. So is it possible that so if you go to the previous slide, if that happens spontaneously, that you actually induce dipole moment spontaneously without the electric field, simply because now you can, well, if the system was stable, you can lower the energy so on average, it's like in a ferromagnet, on average, the magnetic moment or electric dipole moment averages to 0. It's on average 0. But then you can have spontaneous symmetry where if you were to break the induce, let's say magnetic moment, then you gain some energy. You can lower the energy from the, ferromagnetic exchange interaction. So I'm wondering whether here, similarly, you can get where even without the electric field, you can induce, the system spontaneously chooses to electric dipole moment, so then it can take advantage of this attractive dipole interaction.
So Leo, my take is that, well, in the magnetic field, the symmetry break, spontaneous symmetry break is, the magnetic moments are in fact always there. They're just random. And so you can have two magnetic moments coming together, right? In the electrical dipole moment regime, if you don't apply electric field, you would require the two dipoles to be very close to each other. If you're talking about, in the end, of course, the van der Waals interaction comes from spontaneous breaking of the dipole-dipole interaction. That's how van der Waals interaction comes about. But that's not a long-range dipole interaction.
Yeah. The molecules are spherically symmetric without an electric field, so there is no way that they can have a net dipole moment. You have to.
But they can break symmetry spontaneously in the same way.
How? I mean, you have to induce a matrix element, and this is only induced even by a superposition that you create, like Jun is saying, or by applying an electric field that couples different rotational states, and the ground state is a superposition of different rotational levels.
Well, one thing to remember in practice here, Leo, is that actually the energy scale for the separation of the different rotational states is huge. So the ground state is just everything's going to be in the ground state of these molecules, which is spherically symmetric. If you could push to a really, really dense regime of molecules where the interaction strength was larger than the rotational splitting, then maybe something like this could happen. Yeah. But we're like,
that's what I had in mind.
Oh no, this is gigahertz energy splitting, whereas the collisions are the most kilohertz.
And you can think of, again, Leo, I think you can think again about the molecular binding process, like this van der Waals interactions, right? It's, in the end, it is dipole-dipole interaction giving rise to the van der Waals, but you needed the distance between the molecules to be in the range of so-called van der Waals range.
Yeah. So I remember making an estimate that it required too high of densities to have this spontaneous transition. But
exactly. So
otherwise, yes, it's practical.
The interaction will be confined to within two molecules or two atoms, but not on the whole system.
Mm-hmm. Okay, makes sense. Okay.
So there is another question in the chat, Jun. He's anticipating. I think Michael is asking. So this is the motivation to go into pancake traps, hoping to align all the molecules so they only have side-by-side collisions. I mean, he's
yes. Mm-hmm. This excellent, Michael. Yes. But I will give you a surprise. It turns out we want to go to the dipole into the pancakes, but turns out once we learned to live there, we can come back to 3D and still be long-lived. So that will be the surprise. If you don't get bored by the end of my lecture, if I get to that point, I will tell you that we can actually not go back to 3D and be long-lived, because we went into the 2D and learned how to survive, how to swim. So, again, I want to thank the summer school is organized by our theory colleagues, and just want to recognize the importance of the theory colleagues in our work. They have been talking about this since the beginning of the century, and it's literally true. They have been writing papers about dipolar physics in 2D, and I think without they're constantly like, why don't you do this? Why don't you do this? Sometimes it's kind of annoying, like, oh, I have to bolt this vacuum chamber together. I can't do that tomorrow. But it's this constant inspirational and push, and I would say intellectual challenge from our theory colleagues that finally, I think, made this breakthrough. So this is really the reason why we do dipolar physics in 2D. The idea is exactly as Michael mentioned, is to make sure that you can have side by side, because up to this point, you understand now what hopefully is fairly simple explanation. I just don't want to get rid of this head to tail interaction. So I want to suppress chemical reaction. I want to study 3D to 2D transition. I want to get to a regime where elastic interaction finally dominate over inelastic interaction. So dipolar physics will thrive in the 2D landscape. And this will allow you to do dipolar evaporative cooling. This will allow you to see dipolar mediated collisional resonances. And the surprise at the very end, the latest thing, is that we can now come out of the 2D, going back to 3D, and because we are brave enough now. And in fact, the molecules survive there once we found these collisional resonances. And we also recently were able to study dipolar exchanges between pancakes and so on. So there's a lot of interesting physics it's going on. I think actually I have only half hour left, right? Yeah. I may not be able to finish the molecule today, but that's okay. This is actually more fun. There's a lot of exchange.
There are a lot of other questions. It said, I miss, is Nyung Hong, I missed the point why the head-to-tail collisions is inelastic. Could you explain it again?
Head-to-tail interaction is not inelastic. It's all about how you interact, how you arrange yourselves in the long-range physics. So head-to-tail is attractive. Attractive doesn't mean it's a loss. Attractive is a part of interaction. Just like interaction can be positive or negative, they're all elastic. The problem is once you get close enough, there's a chemical reaction waiting for you. There's a black hole waiting for you. So if head-to-tail is attractive, as I mentioned earlier, it overwhelms the reactive barrier, the centrifugal barrier, which was repulsive. Once you get overwhelmed, these molecules just go behind, can you see my cartoon? My mouse is trying to indicate the pathway for it to get into that black hole, and you react away. So it's all about in the long range. Can you keep the molecules at long range? They're strongly interacting, but do not get too close to each other. Then you find out it's bad situation. Does that make sense?
Okay. Yes, that makes sense. Thank you very much.
Head-to-tail itself is not describing loss or not, right? It's just attraction. Okay.
Okay. So the middle region of the black hole, is that where it combined to the K-rubidium star?
Yeah, that's right.
Okay.
Don't take it too serious of some of the words I use when I say black hole. I didn't really mean black hole. It just means it's so unpleasant and something's going to happen. But for chemists, of course, they live for that. So it's all about chemical reactions. So it's all dependent on your perspective.
Okay. Thank you.
Sure. Anna Maria, is that good?
Yes, perfect.
So, okay, well, let me, this is just an experimental apparatus. You can see that a little vacuum chamber in the middle between the two slides, looks like a microscope slides if you have done biology experiments, but those are actually, in fact, electric field coated electrodes, and they happen to be transparent for light to go back and forth. And all together, you can see there are 6 electrodes, like there's 4 rods and 2 parallel plates. The reason is because we can then use this electrical field combinations to basically create arbitrary electrical field directions in space, but also gradients. So we have this incredible control of the electrical field inside the vacuum. And the reason I am spending this time to explain to you this kind of technical detail, maybe you feel that's not so interesting. Well, if you look, the magnetic field control that brings this Feshbach resonance has made all the difference in atomic physics, right? And being able to control interactions. And I want to make this emphasis that being able to control electric field, if you're dealing with molecules, and in some ways, Rydberg atoms as well, right? Being able to control the field that you need to control these molecules are super important. And that's part of the reason why this new experiment that we built back in 2016, 2017, had this bells and whistles built into this intra-vacuum system. And now you can look at these 4 electrodes, and we can place a stack of pancakes in the middle of these electrodes. The DC field can be tuned between 0 to 15 kilovolts per centimeter. And we actually can control it better than 100 parts per million. In fact, recently, 10 parts per million. We can control the gradient and also the curvature. We can also rotate electrical field with angle theta. At the same time, we can apply microwave field with these electrodes. So these are really well designed. I'm actually very proud of the electric field design in this case. And so then we create a bunch of optical lattice traps. As you can see, the optical beams are going through, and we have various different kinds of optical lattice. I'm not going to bore you with actual details, except that finally we'll be able to create a stack of pancakes with a 540 nanometer spacing. And you can actually also image them one layer at a time. And recently, we can actually select a single layer out and do molecular spin. We can actually make each layer have different spins on it. And so I'm going to tell you that. So first, suppression of inelastic loss. Well, here's a curve you have seen before, the density of molecules as a function of time. And you can see now they live pretty long time, a few seconds. And we can actually, this is actually happening in the wall of the electric field. Now we can tune the dipole moment because we can tune the electric field. So as we tune the electric field, you can see that when the dipole moment reaches 0.2 dBi, the two-body loss rate coefficient beta gets suppressed by a factor of 3. At this particular location of 0.2 dBi, it turns out we can already reach inelastic collision rate at the ratio of 200. So elastic starts to dominate over inelastic interactions. And how do we know? Well, we can do this experiment called a cross-dimensional thermalization.
Yeah, just Jun, just to connect to Eric. Eric was talking about the same thing this morning. So for the students to realize when he was talking about evaporative cooling, I mean, how to create the BC, he was talking about the 3-body versus 2-body inelastic, elastic.
Thank you, Anna Maria. And it's really fascinating, right? You know, all of this is trying to get into this particularly favorable regime where elastic collision is what's needed to share the thermal energy in the system, while inelastic is taking you out of the system. So you want elastic to be dominating over inelastic if you want evaporation. But more generally, if you want to just study condensed matter physics, you obviously want the system to live there for a while before they all get killed by some chemical reaction. So that's why elastic over inelastic is really the key point, not necessarily for evaporation, but it's really for many of the experiments we want to do later with condensed matter sort of an inspiration in mind. So we do this cross-dimensional. Maybe Eric also described this. You can actually squeeze one dimension and the temperature rises along that dimension. And
Not yet.
He did. So I can be really fast. Thanks
not yet. No, not yet. No.
Not yet. Okay. So in this particular case, for example, if I have a harmonic trap, look at the circular, I squeeze along Z, as you can see in this cartoon, and the temperature in Z will rise just because it's adiabatic. But then if the system is thermalizing, then the temperature along X direction, even though I have not done anything, should also rise because they are connected with Z directions because the particles are transferring energies back and forth. So we can look at that so-called cross-dimensional thermalization and look at the temperature Tx, how it reaches the equilibrium with the temperature of Tz as a function of the dipole moment. As you can see, when the dipole moment is 0.1 dBi, it takes almost a second to thermalize. When it goes to by just a factor of 2, it's thermalized within 100 milliseconds. And so that's very dramatic. That's because the dipolar interaction scales very quickly with dipole moment squared. And so if you look at the thermalization rate as a function of dipole moment, indeed, you can see that if we increase the dipole moment from 0.1 to 0.3 dBi, the thermalization rate went up by 2 orders of magnitude. And this is actually remarkably what theorists John Bohm, Govan Criminaire have been predicting. They said as the dipole moment increases, the elastic collision rate should increase as this orange curve, and inelastic should be suppressed by this dashed line. And this is exactly what we are seeing, that elastic collision rate rise up from 0.1 dBi to 0.3 dBi very, very quickly, while the reaction rate is being suppressed or at least being held at bay. Therefore, you now can get into this very favorable regime where elastic over inelastic is a factor of 100 larger. And it's all because before dipole moment is established, this actually is another interesting moment to reflect Leo's question. Before you apply any electric field, the molecules don't have a dipole moment, and they just do not interact very strongly at all. So you see from zero divide to go to 0.1 divide. This is rising like semi-log scale. This is rising by many orders of magnitude here, 3 orders of magnitude, just by raising up the dipole moment to a feeble 0.3 divide. So that's really tells you how effective this tuning knob of electric field is. And so once we have that, we can actually use dipoles to assist the evaporation, because now the dipoles are interacting with each other. The molecules are no longer being lost, except they see each other's presence. They can get thermalizations with respect to each other. And we can play tricks. We can actually use electric field. We can create this with optical trap. We can actually use electric field gradient to bend the optical trap. So then the fast molecules, Eric probably talked about that, like it's called a evaporation cut. You make the trap weaker and weaker. Here, not without lowering the optical trapping power intensity. We actually just bend the electric field gradient to make the trap out of shape. So the hot molecules gets escaped. And when the hot molecules gets ejected, it's colliding because it gets the hot, because it's colliding with the cold molecules. And so the cold molecule gets stay put, and you can start to do this very, very efficient evaporation. And what we plot is, for example, the temperature as a function of number, or number as a function of temperature in 2 dimensions. You want the best evaporation is when you have molecules or atoms, the number to be preserved, but temperature goes down. That's always the most greedy criterion. I just want all my molecules stay put, but temperature goes down. Of course, you have to lose some molecules, but you want this ratio to be as favorable for you as possible. In 2 dimensions, turns out this ratio needs to be, the slope log scale should be like 2. And we are at a scale of 1. So you can see it's much more favorable to keep the molecule number intact when temperature is coming along, from 0.2 microkelvin all the way to 40 nanokelvin without losing tremendous amount of molecules, losing 6 times molecules and so on. So this is telling you a very efficient slope. And so with that, we were actually able to evaporate molecules. Like we already created molecules in degeneracy in 3D, but when we load into the 2D, the loading itself had some molecular loss, had some subdivide out to individual pancakes. You lose some, and you add some entropy to the system. So the molecules were no longer degenerate in 2D pancakes, individual 2D pancakes. But because we can do this evaporation now, we can actually get this system back into degeneracy. And this picture on the right-hand side is actually the most striking one. As the temperature gets lower and lower, you start to pick up extra energy because of Fermi pressure. And in 3D, you actually need to get to the so-called T over TF 0.6 when you start to see the curve bend up. You start to see appreciable Fermi energy only when T over TF is less than 0.6. But 2D, because there are fewer density of states, this transition actually happens sooner. At a T over TF 0.1, you already get into the quantum degeneracy because you start to see the excess energy due to the Fermi pressure coming up. Okay, next I want to tell you a little bit of controlling the reactions now with electric field. So this is all good. We are controlling the reactions by making elastic interaction really dominating over inelastic. But here I'm going to introduce a collisional resonance, which is actually really interesting. So what we do is we can actually use electric field to orient the molecules to be perpendicular to the pancake. I think that this relates to the question Michael was asking. The thing is, when experiments start to work really well, you become more and more, you can become more brave. And so the degree of braveness is reflected in the fact that we're not there to turn the electric field to be in the plane of the pancake. And so you can see this is like a worst case scenario. These molecules are going to have head to tail interaction. They can still also have, of course, side by side, but you have the electrical field is now lying right in the plane. So you have all these loss channels opening up. But the thing is, this temperature is already so low, and we have the system under watchful eyes. We're controlling it. So we were able to just turning this electrical field from perpendicular to the pancake to parallel to the pancake, and actually just watch the reaction rate as a function of this angle. Even at the best angle, of course, is 0 when it's perpendicular, but even at 90 plus minus 90 degrees, the reaction rate went up by a factor of 20 or so, but it's still within experimentally measured quantities that we could actually understand it. The reason I'm telling you this is I'm soon going to get into
There is a question about I missed this, but why does the dimension enter into the good evaporation criterion the NDT is smaller than D?
Oh, it's just the phase space density calculation. So in 3D, this should be 3, and in 2D, it's 2. It's just when you calculate the 2D density and the temperature. Remember, phase space density is where you needed the temperature to be sufficiently low and the density to be sufficiently high, such that quantum mechanical waveforms, the Broglie wavelengths of each individual particles overlap with each other. And the Broglie wavelength is scaled with the temperature, right? Inverse. And then the density scales with interparticle distance, and therefore both enters into that relationship. It's just dimensionality just comes into regulating the spatial density in the system. Okay. Again, those are well, we can provide material for you too. These are like in the standard textbooks of quantum gas, a phase space density.
Okay, that's clear. Yeah.
All right. I'm going to tell you about this particular story now, the molecular energy tuned with the electric field. So this actually lies on some of the early questions you guys were asking. So if I create a molecule in the absolute ground state, 0, 0, there is no dipole moment. It's a single quantum state. If you apply a little electric field, well, you can certainly apply microwave. You can transition. You can put them in coherent superposition between n equals to 0 and n equals to 1. N represents the rotational quantum number. So you can prepare coherent superposition. You can apply electric field. When you apply it, 0 state, n1 state start to be mixed. They have opposite parity. If you write down the matrix element between 0 and 1, and you put it, R, ER in the middle, you actually support a dipole moment in there. And therefore, you can drive it with a microwave field. You can apply DC electric field, the state actually start to repel each other. But of course, we also know there are rotational ladder that Kaden mentioned earlier. There's a 0, 1, 2, 3, right? All these states, in fact, will be affected by the electric field. So if I put my molecules into the state of 1, 0, and I apply electric field, this 1, 0 population also sees the mixing with an n equals to 2 state, because between 1 and 2, there is also a matrix element that's non-vanishing. They also have opposite parity because 0 and 2 have the same parity. So there's another dipole moment, coming up. All I'm saying this is as you tune the electric field, eventually, initially you see 0, 1, and 1 and 2, the energy spacing is very far apart. But if you tune the electric field large enough, you could actually get into the regime where two molecules with 1, 0, 1, 0 can be tuned into unresonance with two molecules with 0, 0 plus 2, 0. That's a significant modification of the rotational energy spacing. But with our electric field that we introduced, we can actually do that. And then, of course, there's also a possibility where you can actually have 1, 0, 1, 0, two molecules prepared in 1, 0 state under the electric field happen to be energy degenerate with if a molecule in 0, 0 and 2 plus minus 1. What does that tell you? Well, what this tells you is, yes, there's a question?
No, Jun. So we are reaching the 10 minutes, 7 minutes to go. So maybe try to wrap up to allow for some questions, or do I continue next time? next lecture.
Yeah.
Sounds good. Yeah, so maybe let me just finish, like give me 2 more minutes. I will finish this slide and the next slide, and then I will stop.
Mhm.
Okay, so here's an energy landscape of, if you plot these 2 molecules, starting at the 1010 as a function of electric field. The 1010 molecules, the energy is rising with electric field. But then if you put a 00 and the 2 zeros together, their energy is decreasing. At a certain electric field, these energies cross. That's called degeneracy. And when your energy is crossing, well, the molecules have dipole interactions. So the molecules can make the dipole-dipole interaction, can make this crossing to be avoided. This again, when you have a 2-level system and you put an off-diagonal element to create interactions, you can actually create this off-diagonal interaction, create this crossing in your 2-level system. So again, these 1010 molecules and the 0020 molecules can be resonant, can be bring onto resonance, and then where the dipolar interaction can have a bigger consequences because the energy being avoided. Maybe that's a good point. I stop because this is going to have consequences of reaction resonances when the molecules coming together, whether they are from energy scales, which is at a large electric field or the lower electric field, how they approach this crossing point can have a major consequences of whether the reaction is allowed and in fact enhanced versus the reaction gets completely suppressed. And so in that regime, you can actually have molecules. We first explored this in 2D, but then we can actually explore this resonant behavior in 3D and create the situation where even in 3 dimensions, the reaction is shielded. And that we can discuss on Wednesday. I think I will stop here, maybe.
Sounds great, Jun. Thank you for the very, very nice lecture.
Thank you.
Thank you,
So
Jun.
we have some time for questions.
Should I maybe unsharing this so that people can see people's face?
Sounds good.
Yeah, perhaps, yeah. Well, also you can go to the view where the speaker, you're viewing the speaker rather than general gallery view.
Yeah.
It's in the upper right.
That's weird. I'm sorry, Leo. And you don't see the sharing anymore, right? Oh, you still see?
No, I still see the sharing.
Okay.
Yeah, perfect.
Yeah. So if you have questions, please, I would be happy to discuss this. Anything that's unclear so far. Then on Wednesday, they actually have some new results that we'll share with you by this collisional reaction resonances and how the spin exchange is happening between pancakes and so on. So once you remove the reactional loss and being able to tune the interaction with dipole moment with electrical field, suddenly this really opens up.
So you talked about this a little bit, Jun, but could you elaborate a little bit on, if my goal is to see dipole interaction physics, when would I want to look at molecules versus Rydberg atoms versus magnetic atoms versus other things? And you mentioned the controllability, but can you just elaborate on your thoughts on this?
Yes. So it's always comes down to controllability and how long the quantum, in the quantum computing language, it's the circuit depth. How long can you make the operation coherent over the time scale the quantum system is alive? So, this actually could be an underlying theme to these different quantum systems complement each other. Let's say magnetic dipole versus electrical dipole. If I can have my molecules live there for a long time compared to the magnetic atoms, I would prefer, because I've been working with molecules, with the molecular system, just because the interaction is stronger. I can make more operation. I can have more operations per unit time when the quantum system is living there together. and also the capability of having the system being tuned up from completely zero. There's no dipole interaction whatsoever. When I don't want it, I can just turn the electrical field off. There's no interaction whatsoever. So I can bring the system quenched into a particular subspace of a Hamiltonian and bring them together, bring them there without any cost and almost no energy cost. And that's another really interesting aspect of that, strong and yet precisely controlled. Compared to Rydberg atoms, talking about strong, Rydberg is even stronger. Some of the Rydberg atom dipole interaction you have heard of, they can be much, much stronger than molecules. But remember, the Rydberg states are not long-lived. And typically when you excite them there, you have to worry about, so far all the experiments people are doing is use Rydberg excitation to do the so-called blockade experiment. You actually do not go up there. They are using that interactions to create some sort of entanglements and so on. And that's powerful. But if you want a quantum system that's living there, that's actually part of the evolution and so on, molecules has pros and cons, because it's in principle coherent, it's living there forever. If you really solved all these reaction problems, especially later I will tell you about individual molecules in optical lattices and so on, when only spins is moving around, but the molecules themselves as a physical system, they actually are confined in individual lattices. So you can have a long coherence time that remains to be experimentally or demonstrated putting all these bells and whistles together. But potentially, that's a quantum system that you can actually study its evolution tracking over a long period of time.
I have another question. Well, it's very basic, but I think I kind of missed when you go when you turn from the S wave scattering to the P wave. The P wave where you have that barrier that depends, that the rate of the density over time depend on the on temperature. While in the S wave you don't have that. But and then you change the spin of the molecules to do that. But I'm not sure what actually changed. Like, what do you control when you turn the S wave into the P wave?
Okay, yeah. Remember when you write down wave function, so you suppose you have two molecules, and then when you write down their wave function, if the two molecules are distinguishable, molecule A and then molecule B. They're labeled by their individual spins. You can keep track of it. Then when you write down the wave function, you do not need to write symmetrization. These two particles can be separated, yes? And so when they come close, you do not have to symmetrize the wave function. Now, if I make these two molecules completely identical, so when I write down the wave function, I have to write psi A, psi B, plus minus psi B, psi A, yes? Because it's symmetrical, yep. Right? And the reason plus or minus, you have two choices. It depends on whether those are bosons or fermions. If they are bosons, like what you heard about this morning, the sign is plus. A, B could be also BA. If they are fermions, you have to be a negative sign, because as we learned, the Pauli exclusion principle or Fermi statistics, when they exchange the particle positions, there has to be anti-symmetrized. And so that's really the everything you need to know in terms of why the S wave and the P wave have a difference, because that negative sign change means that if you had angular momentum associated with the two particles circling around each other, if you have 0 h bar unit of angular momentum, meaning the two particles can approach each other directly, then you don't have the centrifugal barrier, but that process would not be allowed if you have to anti-symmetrize the wave functions. In order to anti-symmetrize the wave function, you have to circular. You have to have at least 1 h bar unit of angular momentum. And that circular motion, I'm sorry if I'm making you dizzy, because my hands are moving around like this. That 1 h bar unit of angular momentum gives rise to the centrifugal barrier. And so all we were doing, now you were asking, what did I do? Then as if pulling a magic trick on you. it's all we are doing is just making the two particles having the same nuclear spin or different nuclear spins suddenly. And that's why it's so nice, the quantum mechanically. As soon as you do that, the nature says, oh, the two particles, I cannot tell them apart. I better put on this barrier of the P wave because these are fermions. If those were bosons, the consequence would be actually very different. They would be attracted to each other more strongly than distinguishable particles. So this is actually, when you study quantum optics, the early days when people dealing with thermal light versus classical coherent states, you'll see this factor of two difference in the so-called function effect and so on. It's all related to the same physics, called quantum statistics of particles. So it's really fascinating to read about it. I think the Boulder School is actually a great opportunity to go back, read some quantum optics literature, and they are connected, of course, to the matter waves and so on.
And we will have some specifically quantum optics focused lectures in week 3 from Alexei Gorshkov. So
yeah,
there'll be a good chance to connect there.
Other questions?
Let me ask you guys a question. Is the pace that I was giving, is that reasonable? Or that's way, way too slow or way too fast?
It's definitely not too slow. I think it was, from my perspective, I think it was pretty good and relaxed, but we need to hear from the students. So Alex just weighed in.
And one says they like the pace. If everyone wanted their little on the reactions, there's a slower and faster. So you're welcome to all hold up your reaction. And if you like the pace, just click the yes, I guess. There's a yes reaction. We have one.
I really like that feedback from you because that way I can adjust myself a bit. Like I said, before I came into this lecture, I prepared way too much material and I couldn't finish my today's lecture. But fortunately, Leo was kind enough to give me 2 lecture slots. I can at least finish my first lecture and I can do whatever I needed to give you a little hint about clocks. And again, I want to make a connection to the molecule work with clocks.
That's good.
Good. So it went down, but I did see 5 or 10 at least goods, and I didn't see any slower or faster. So I think you're hitting the pace right.
Okay.
I don't want to be guilty of holding anyone hostage because I know it's a little past time, but I guess, so I had a question on the 2-body loss graph where you show as a function of applied electric field that you have this dip at like 0.2 dBi.
Yes.
This is for 2 ground state molecules. Is this graph significant? Or so it goes down and then it turns to go back up again after applying more electric field? Is this pattern shown for like 2 rotationally excited molecules as well? Like is the 2-body loss rate for a population of all rotationally excited molecules going to look the same? And Michael, in particular,
you're asking this plot, right?
Yeah, where you show this dip here. And then also, as it goes to the rotationally excited molecules, you showed where this avoided crossing happens at like 12 kilovolts per centimeter, where maybe naively, I think the 2-body loss rate is quite high there. So, but
these are actually excellent questions coming from almost like an expert. So you may have studied the molecules a little bit, but let me provide an answer to the first question. And if it's getting too late, Leo, you can stop me because we can continue to explain this next lecture. But this is actually very, very excellent observation. Why this suppression has a minimum? If this picture of having these molecules stacked up on a single individual pancakes, and you apply electric field, this dipole moment gets stronger and stronger. You would think the 2-body, the interaction, which is repulsive, the repelling each other, side-by-side interaction gets stronger and stronger. So they should only get better and better, right? Now, why the heck it goes back up? It turns out, and actually it's a complicated story, even in the single pancake, the reason that, you can think of these pancakes actually has finite thickness. And that finite thickness which is a confinement energy along the z-axis, along the direction where the EV field is being applied. If you have infinite laser power, you want to make this direction, this z direction, to be as strongly confined as possible, where the energy scale is far beyond any dipolar interactions possible. In that case, you will see this goes down further and further and further. But now that we have seen, actually, I was going to say, now that we have seen between the two pancakes, the molecules can actually spin jump back and forth. I'm actually not so sure, the picture I just described to you works for a single pancake. But when we have a multiple pancakes, there may be extra complications here. But within the single pancake, there's also a complication. If the confinement is not sufficiently strong, meaning there is energy associated with the confinement along this particular z direction.
Right.
As you apply the electrical field stronger and stronger, where the dipolar interaction becomes comparable to the energy scales of jumping between these, along this tightly confining directions, they can overwhelm the fact that that's why we call it quasi 2D. It's not a strictly 2D system. And that's where you can see the bending back up. And this bending back up can be pushed back down if we were able to apply a deeper lattice, as I explained earlier.
I see.
But so this is only from the single pancake. I actually think with the multiple pancakes, the story might be even more complicated because there could be an inter-pancake interaction. Now we have seen this effect in the experiment.
I see. Thank you.
So it's actually a very deep question. In fact, a couple of weeks ago, Wolfgang's group is getting into this 2D physics, and he and I were discussing about various different approximations one make if you read early theory papers, they actually show this very gentle curvature as well.
I see. And so this, I guess, this doesn't seem like it would be mitigated or changed by being in different rotational states.
That's correct. Yeah,
Right.
This is actually, yeah, you actually mentioned this. The molecules are in the absolute ground state of rotational excitation. They're in the ground state. You go to the excited state, the dipole moment, actually, that's something, n equals to 1 state, the dipole moment is actually smaller than n equals to 0 because n equals to 1 guy is being sandwiched by 0 and 2. So,
Right.
so it's being pulled apart a little bit. And so the dipole moment is actually smaller. We see exactly the same effect n equals to 1 if you scaled with the dipole moment that's being induced on n equals to 1 state. But n equals to 1, all the physics can be scaled with n equals to 0 as long as you have a reasonably separated energy scales, like rotational energy scales out of the question and so on. Then it's just the dipolar physics.
I see. Thank you. And I guess the last technical, can you source the microwaves to drive rotational transitions from those electrodes that you're making the DC field with, or do you have to apply something else?
Yeah, actually, that's exactly right. Those 4 electrodes we applied, those were serving both as a DC field as well as a microwave field. And on Wednesday's lecture, I will show you some of the experiments that these pancakes, we cannot apply electrical field gradient. So each pancake is sitting at a different electrical field environment. And then we can tune the microwave, and you can actually flip the spins 1 pancake at a time. And, and therefore, we can actually create any arbitrary combinations of spins in different pancakes and watch how they interact with each other. So yes, I think, one thing you learn in E&M class is if the scale of size is smaller than the wavelength of the microwave field, then the microwave field is just, the distribution of microwave field is the same as the DC electric field, right? So we are using that advantage. We're basically taking advantage of that to do both microwave and DC control.
Great, great, thank you so much.
Now we are over time for sure.
Yeah, so maybe this is a good time to wrap up. So let's thank Jun again for a wonderful first lecture. And we'll reconvene tomorrow at 9 a.m. Boulder time. Thank you so much. Thank you, Jun.
Thank you. Thank you.
Thank you. Pleasure.
See you.
Bye-bye.
Only 19 days left of this, so thanks for the great first one.